Hi everyone. In this video, we are going to discuss about the polar coordinate system. We already know the Cartesian coordinate system, which is a rectangular coordinate system. Here, the polar coordinate system is actually a circular coordinate system. As you can see in the diagram, the coordinate pattern all looks like concentric circles there, right? So now, as in the Cartesian coordinate system, we had an origin and then x-axis, y-axis. We had two rectangular axes and we had the origin in the Cartesian coordinate system. Whereas in the polar coordinate system, we have something called a pole, which is more like an origin. Here, it's called pole. The point O right here at the center, that's the pole. And OA, which is kind of the positive x-axis here, it's called the polar axis or the initial ray. So OA is called the polar axis or the initial ray or the initial position of the ray. We can call it initial ray anyways. And then if we have a point P, which is kind of right here, let me highlight that with a pink dot right here. Let's suppose this is the point P, and the point P's coordinates can be denoted as r, theta. Now what is r? Well, r is the distance from pole to the point. It's a straight line distance and it's actually called the radius vector. So r is actually called the radius vector. And what is theta? Well, theta is the angle of rotation of the ray from the initial position to P. So from the initial position of the ray, we have rotated it by a theta angle in the counterclockwise direction, and that is the angle theta. So in the coordinate where you say P within parenthesis r, theta, r is the radius vector and the theta is actually called the vectorial angle. Now there are sign convention on theta. So theta will be considered positive if the ray is rotated in the counterclockwise direction or the anticlockwise direction. To reach the point P, if the initial ray is rotated in a counterclockwise direction, then theta will be considered positive angle. And if the initial ray is rotated in the clockwise direction, then theta will be considered a negative angle. So that's the sign convention of theta. Now there is also a sign convention of r, and that is very important. We need to clearly understand it. So let's try to talk about the sign convention of r. The sign convention of r is kind of like this. When r is measured along the ray from the pole, then r will be considered positive. Now if the distance of the point is measured in the opposite direction of the ray from the pole, then r will be considered negative. Now we'll take an example to see how the sign convention of r works. To clearly understand the sign convention of r, let's look at this diagram. Suppose we have a point P and we have to determine the coordinates of P in terms of the polar coordinates, right? So now what would be the coordinates of P? Well, first would be the r. We have to determine r, and that would be 1, 2, 3, 4, 5. So looks like we are moving 5 units from the pole along the ray, and let's assume that the ray has been rotated by an angle theta. And in this case, obviously theta is equal to pi over 4, because if you look at the polar coordinate system here in this diagram, that particular line is actually pi over 4. So the rotation here is pi over 4 or 45-degree rotation in the counterclockwise direction. So theta is being considered positive. Now how about the r? Well, r is actually, you can see we are moving 1, 2. So let me highlight that with a yellow dot maybe. So this is the 1 unit right here, and then 2 units, and then 3 units, and then 4 units, and then finally we reach the point P, which is actually 5 units away. So in this case, r is actually positive 5. Why? Because we are counting the distance of r from the pole along the ray. Now along the ray we are measuring, so that is why we have to take it as positive. So then the coordinates of P would be something like this. It would be, r would be positive 5, so that is 5, pi over 4. That's the polar coordinate of P. Now if we had a point Q right here, let's suppose that we had a point Q over here, way down below right here. I'm writing right here. So suppose this is our point Q. So what would be the coordinates of Q in terms of polar coordinates? To find the coordinates of Q, first we have to see how much is the rotation. Well, in this case, the rotation is kind of like this. Let me denote that with a blue color maybe. So this will be the rotation. So in this case, theta would be actually 5 pi over 4. So theta in this case, I would say for the point Q, theta is actually 5 pi over 4 because it's counterclockwise rotation. And always remember, this rotation is of the initial ray, which is the OA. So if we rotate the initial ray, then we finally arrive at the point Q, then the rotation here is 5 pi over 4, and that should be positive because the rotation is in the counterclockwise direction. Alright, now how about R in this case? Well, in this case R will also be 5 here, as I have taken the point Q, so this should be 1 unit, then 2 units, I am doing a yellow dot, 3 units, 4 units, and then obviously we reach the point Q, which is 5 units away from the pole along the ray. So then Q's coordinates would be kind of like this. We can say this will be 5, 5 pi over 4. Now there is another way of denoting Q's coordinates, and that is where we are going to learn the sign convention of R. Now, if we simply rotate by pi over 4 angle and we go for 5 units, you are thinking that we will reach the point P. That is correct. We will reach point P, but somehow we have to reach point Q. So what we are going to do, let's rotate only pi over 4. So now I am going to write Q's coordinates like this outside here. So say suppose Q's coordinates, I want to denote it with a rotation of pi over 4. And is that possible? Well, let's see. I want to denote that with a rotation of pi over 4. So if we rotate only pi over 4, we are going to reach the point P, not Q. Well, then how do we reach point Q? Well, if we go in the opposite direction of the ray, like you see, at this time with a rotation of pi over 4, we are actually at point P, but we want to go to point Q. So what can we do? Well, if we start counting, or if we start going in the opposite direction of the ray from the pole, and if we go 5 units in the opposite direction, we are actually going to reach Q. So then we can say, well, then this could be negative 5, pi over 4. So with a pi over 4 rotation, we are still able to reach Q. Of course, we have to take R as a negative value because we are going in the opposite direction of the ray. If we go along the ray, we are going to reach the point P, but we need to reach the point Q, so we have to go in the opposite direction of the ray, and then with a pi over 4 rotation, we can still reach Q as long as we measure the R in the negative terms. So then you can see the two coordinates of Q. We have positive 5, 5 pi over 4. Let me write it down again. And they both are the same thing. It's still the same point Q. We can denote it in two different ways. And here you can clearly see the sign convention of R. When R is measured along the ray from the pole, then R should be considered positive, or it should be denoted as positive. And when R is measured in the opposite direction of the ray, then it should be denoted as a negative value. I hope this point is clear, and it's very important actually. We have to be very clear about the sign convention of R. Sign convention of theta is very easy. If you rotate the ray in the counterclockwise direction, then theta is positive. If you rotate it in the clockwise direction, then theta is negative. That's very easy. But for the sign convention of R, we have to clearly understand how R is being measured. When R is measured from the pole along the ray, that is positive direction. And when R is measured in the opposite direction of the ray, then it is negative. Since this is a circular system, we have a very interesting observation here that suppose for any point P, if the coordinates are like this, R theta will be same as R theta plus or minus 2 pi, because if you rotate the ray one full circle, the position of the point is still going to be same, right? So whether you rotate it in the positive direction one full circle, or you rotate it in the negative direction one full circle, the ray is still going to be at the same position. So if somebody says, hey, here is a huge angle R a large angle, right? You can reduce that to a smaller angle by subtracting multiples of 2 pi or adding multiples of 2 pi. So this is one important observation that we should note. Let me highlight this. And another observation is, in this particular example, let's see what are the two different ways that P can be denoted. Well, Q's coordinates we have seen, right? We have seen Q's coordinates, that Q can be denoted as negative 5, pi over 4, or 5, 5 pi over 4. Right? Similarly, what are the two different ways we can denote P? Well, P's coordinates can be denoted also like this. P can be denoted as the positive R, which is 5, pi over 4. That is one of the ways. And the other way would be, P also could be denoted as, if we go for 5 pi over 4 angle, and then if we go in the opposite direction, we can say negative 5, and that could be another way of denoting P's coordinate. I mean, we could go all the way to 5 pi over 4 and then move in the opposite direction of the ray, and then also we will reach the point P. So P's coordinates can be denoted as negative 5, 5 pi over 4, or positive 5, pi over 4. Now if you look at both of these examples, what is the difference in the theta? Well, the difference in theta is actually pi. So r comma theta, this is also equivalent to negative r comma theta plus or minus pi. If you rotate the ray by pi more radians and then take the negative value of r, you will still reach the same point, as we have seen in this example, the p and q points, right? So to reach the point p, instead of rotating just pi over 4, if we rotate pi more radians to make it 5 pi over 4 and then take the r value negative direction, then also we are going to reach the point p. So r comma theta is equivalent to negative r comma pi plus or minus theta. Now in this case, for the coordinates of p, let's see what is the difference. So 5 pi over 4 minus pi over 4, what is the difference? Well, this is actually 4 pi over 4 and that is actually just a pi. So the difference is actually pi, right? So if we rotate pi radians extra and then take negative r, then also we are going to reach the same point p. And now if you consider the negative angle, so far we have seen the positive rotation or the counterclockwise rotation. Now let's take the negative angle. If we go in the negative direction, for example, we could have reached q by going in the clockwise direction. And in that case, how much of rotation is that? Well, that would be pi over 4, another pi over 4 and another pi over 4. So that would be negative 3 pi over 4. So q's coordinates can also be written like this, positive 5 for the r and a negative 3 pi over 4. And now if you see the difference between pi over 4 and negative 3 pi over 4, so that would be negative 3 pi over 4 minus pi over 4. I'm just calculating the difference, and this difference is actually negative 4 pi over 4, and that is again negative pi. So as you can see, if we rotate pi radian extra either in the positive or negative direction of the rotation, we will still reach the same point as long as we take the negative value for the r, as long as we reverse the sign of r. I hope it is clear up to this point. And now we are going to take a few examples and see how we can denote them on the polar coordinate system. Now suppose we have to plot these 4 points on the polar coordinate system P, Q, R and S, and we have their polar coordinates, so we have to plot them on this polar coordinate system, right? So let's first try the point P. Well, P would be at a positive rotation of pi over 6 and 5 units away from the pole. Now where is our pole in this case? Well, pole is right here at the center. And where is the initial ray? Well, let me quickly draw the initial ray. So that's the initial ray right there, and the pole is at the center, and we have to plot the point P, which is at positive pi over 6 rotation, and positive pi over 6 rotation would be this much rotation right here. And where would be the location of P then? Well, P is actually 5 units away along the ray, because it's a positive value. So along the ray 5 units away. Now if our ray is kind of like this, so now after a positive pi over 6 rotation, the ray will be kind of here, and we have to go 5 units along the ray. So our point will be right here. So 1, 2, so here is 1, then here is 2, and then we have 3 right here, and then 4 right here, and then 5, so right here. So that will be the point P. So that's the point P. Why? Because it's a positive rotation of pi over 6 and then positive 5 units, which means along the ray from the pole. So from the pole along the ray we have counted 1, 2, 3, 4, 5. So that's the position of P. Now let's try to plot the point Q. Well, the point Q is at positive 5, negative pi over 6. So we are now talking about a negative rotation of pi over 6. So let's do the negative rotation, and that would be kind of right here. So this will be the negative rotation. If we do negative pi over 6, that would be this rotation right here, this much of rotation. And so where would be the ray then? Well, the ray will be kind of here, and then we have to go 5 units along the ray because it's positive 5, right? So 5 units along the ray, that would be right here. That's the point Q, which is 5 units along the ray, that's the positive 5, and the rotation was negative pi over 6. So that is our point Q right there. Now let's try to plot the point R. Well, R is actually negative 5, pi over 6. So it's a positive rotation pi over 6, and then we have to count negative 5. That means we have to count opposite direction of the ray. Now pi over 6 rotation, we already have the ray here in the diagram, which is the blue ray. That's the pi over 6 rotation in the positive direction. And we have to now move negative 5 units. That means we have to go in the opposite direction of the blue ray by negative 5 units. So that would be where? Well, that would be kind of right here. we kind of went in the negative direction of the ray 5 units to reach the point R, whereas the rotation was a positive pi over 6. So positive pi over 6 rotation, and then we need to start counting, or we need to start moving along the opposite direction of the ray from the pole, and then we are going to reach the point R. That is how we get the negative radius vector. Now let's talk about S. Well, S is a point whose coordinates are negative 5, negative pi over 6. So it's a negative pi over 6 rotation, and we already have a ray like that, which is the light green color ray, which is at negative pi over 6 rotation. But now we have to go in the opposite direction of that ray. Now what would be the opposite direction of that ray? I have denoted the opposite direction of the ray with a dotted line. So we are at negative pi over 6 rotation, and now we are going in the opposite direction of the ray from the pole to measure 5 units. So we are going to reach the point right here, and let me highlight that with a red dot maybe right here. So this is our point S. And let me also write down their coordinates. So S's coordinates are negative 5, negative pi over 6, and R's coordinates are negative 5, pi over 6, and Q's coordinates are 5, negative pi over 6, and P's coordinates are 5, pi over 6. By plotting these 4 points, the concept of negative angle and negative R should be clear, right? Next, we are going to discuss about how to convert between polar coordinates and Cartesian coordinates. Meaning, go from polar coordinates to Cartesian coordinates, or go from Cartesian coordinates to polar coordinates. So let's see how that works. Let's suppose we have the coordinates of point P in the polar system, which is r, theta. And if we are to express that in the Cartesian coordinate system, then how is that going to look like? Let's assume that the polar axis is same as the positive x-axis, and the pole is same as the origin. And let's kind of imagine that this is like, the point P is hanging in the Cartesian coordinate system now. Then how would we reach P? Well, if we have to convert the polar coordinates into the Cartesian coordinate system, then we have to find out the perpendicular distances from origin along the positive x-axis or along the x-axis, and then we have to find the distance from x-axis to the point. So now let me drop a perpendicular from P onto OA, assuming that OA is our positive x-axis now and O is the origin. So if I drop a perpendicular right here, let's suppose the perpendicular lands on the positive x-axis at point Q. So then what is OQ? Well, OQ would be the x coordinate of P, and if you were to write P as x, y, so now I'm converting this into the Cartesian coordinate system. Let's say this is x, y, and let's also join O to P. So this distance would be R from the pole or the origin to point P, that would be R, and this angle would be theta. Now clearly, if we have to denote the coordinates of P in the Cartesian system, then x is actually equal to OQ. So the x coordinate right here that I have written, this is actually the OQ distance, and the y coordinate is actually the PQ distance or the QP. So I can say the y coordinate is actually the QP distance. Now let's try to find out what is OQ in terms of R and theta. Well, clearly you can see that OQ over R would be the cosine of theta. So from here we can say that OQ is equal to R times cosine of theta. And what about QP? Well, QP over OP, that would be sine of theta. If we assume the right triangle OPQ, that's a right triangle. So for that right triangle, OP is the hypotenuse, obviously. So then we can say that QP over OP, which is R, so QP over R, that is equal to sine of theta. And from here, obviously QP is equal to R times sine of theta. So clearly you can see our x coordinate is actually R times cosine of theta, and y coordinate is actually R times sine of theta. So P's coordinates now can be written as, in the polar system, if the coordinates of P are R, theta, then that can be written as R times cosine of theta, R times sine of theta. So this is how we convert from polar system to the Cartesian system. Now if we have to convert from Cartesian system to the polar system, then how it would look like? Well, then we need to convert xy coordinate into the r theta coordinate system, right? So from xy system to r theta system, what do we do? Well, first we have to find out the value of r in terms of x and y, and also we have to find out the value of theta in terms of x and y, right? So now let's try to establish a couple of relationships here. If P's coordinates were x, y, then what would be r? Well, clearly we can see that x squared plus y squared would be r squared for the right triangle OPQ. If you think about it, if you denote this as x now, so let's say this is our x now. I'm using a yellow color here. So let's say this is x and this is y. So then obviously x squared plus y squared would be r squared. That's from the Pythagorean theorem. And from here we can say then r is definitely equal to square root of x squared plus y squared. Alright, we have been able to calculate r in terms of x and y. Now let's try to calculate theta in terms of x and y. Now we can see that tangent of theta is actually y over x. And from here we can say, well, then theta is definitely equal to tan inverse of y over x. So if we were to write the coordinates of a point P from x comma y into the polar system, this is going to look like this. It would be P, r would be square root of x squared plus y squared, that is r, comma, theta would be tan inverse of y over x. And based on the sign of x and y, we have to first determine which quadrant that the point lies in. And based on that, we have to determine the value of theta. Sometimes x over y could be a positive value, could be a negative value, and accordingly the value of theta would be tan inverse of that positive or negative value. So theta could be in first quadrant, second quadrant, third quadrant, or fourth quadrant. We should determine that based on the x and y coordinates. Just by looking at the xy coordinates, we can clearly understand which quadrant it belongs to, and then accordingly we can calculate the value of theta. Now let's take a couple of examples going from polar to Cartesian and Cartesian to polar. In the first example, let's suppose we have been provided the polar coordinates of a point which is like this, 3, pi over 4. And this point is clearly in the first quadrant because it's a pi over 4 counterclockwise rotation, and then 3 units from pole to the point in the direction of the ray. So this is in the first quadrant. And now let's try to convert it into the Cartesian coordinate. So what would be x? Well, here x would be r times cosine of theta, and that is equal to 3. In this case r is actually 3, so that would be 3 times cosine of pi over 4, so that would be 3 times 1 over square root of 2, and that is equal to 3 over square root of 2. And similarly, what would be the value of y? Well, y is equal to r times sine of theta. Now in this case r is equal to 3 and sine of pi over 4, and this is equal to 3 times 1 over square root of 2, and that is equal to 3 over square root of 2. So then the Cartesian coordinates of P will be like this. I'm just writing it right there next to the question. So P can be denoted as 3 over square root of 2, 3 over square root of 2. And now if we have to go from Cartesian coordinates to polar coordinates, let's also take an example along that line. Here is our next example. I'm writing it on the right hand side here. So let's say this is our second example where we want to go from Cartesian coordinates. Let's say we have negative square root of 3, 1. That's in the Cartesian system. So x coordinate is negative square root of 3, y coordinate is positive 1. So obviously the point is in the second quadrant. And from here we have to go to the polar system. So we will find out what would be the polar coordinates of this point, right? So let's try to find that out. Now in this case, what would be r? Well, r would be equal to square root of x squared plus y squared. So that would be negative square root of 3 squared plus 1 squared, and that is actually square root of 3 plus 1, that is equal to square root of 4, and that is plus or minus 2. And we're going to use the principal square root value. We'll go along the ray from the pole. So let's take the positive value then. So we'll take the positive 2. And what about theta? Well, theta is equal to tan inverse of y over x, and in this case this will be tan inverse of what is y? Well, y is actually positive 1, and what is x? That is negative square root of 3. So this will be equal to tan inverse of negative 1 over square root of 3, and that would be 5 pi over 6 in the second quadrant, of course. So we have found the polar coordinates now. R is 2 and theta is 5 pi over 6. So we can write it as 2, 5 pi over 6. Tangent ratio is negative in the second quadrant and the fourth quadrant. So when determining the value of theta, we have to be careful, right? Whether we want to pick the theta value from the fourth quadrant or the second quadrant, that will depend on where the point P belongs to, right? If the point P belongs to the second quadrant, then we have to pick the suitable value of theta, which will be in the second quadrant. And in this case, the suitable value was obviously 5 pi over 6. That gives us tangent of 5 pi over 6 would be negative 1 over square root of 3. So tangent inverse inverse of negative 1 over square root of 3 became 5 pi over 6, and that's the value of theta. So that's a positive rotation, 5 pi over 6, and then we go 2 units along the ray to reach the point P. This brings us to the end of this video. I hope everything made sense. Thank you for watching. See you in the next video.